So in this lecture video, lecture number 15 in an introductory class in electricity and magnetism, I'm just going to introduce the concept known as capacitance. And capacitance is often, well, typically given the symbol capital C, and you cannot confuse it, so not to be confused with the Coulomb. So lots of capital C's around. But what a capacitor is simply an arrangement of conductors. And the conductors don't necessarily need to have electric charge, but they can. But the point is a capacitor is about the conductors. It's about the conductors. You can make a capacitor out of a single conductor, and you can make a capacitor, and this is the more typical example, out of two separate conductors. And in particular, and I'm going to belabor this point later in the video, but what a capacitor does is, among other things, honestly, there are other things it does as well, but to start with, what a capacitor does is it stores charge separation. I think I tend to belabor this point more often than any books do, but I believe that it's an important distinction. What it does is it stores charge separation. Yeah. Okay, so the definition of capacitance, there's a definition, like a defining equation. And what this equation is the capacitance is equal to the charge separated, so that's the charge separation that I'm talking about, the charge separated, divided by the potential difference. So this is how you would calculate capacitance. You could calculate the capacitance easily if a problem just told you it takes 10 volts to store 2 coulombs of charge separation. Then 2 coulombs divided by 10 volts is 1/5, and it'll be 1/5 of a coulomb per volt. But the SI unit of capacitance is called the farad. So in this previous example that I just sort of said, I would be talking about 1/5 of a farad of capacitance. So this is the name of the SI unit of capacitance. And the SI unit is built out of other SI units. Since we're talking about charge divided by voltage, right? Or charge divided by potential difference, the SI unit of charge is the coulomb. The SI unit of potential difference is the volt. So the farad is a coulomb per volt. So yeah, so I'm going to describe some of this. I'm going to give a couple of examples of calculating the capacitance if you know the charge separated and the potential difference. But then I'm going to show you that you can actually, even if you don't know the charge and the potential difference, you just know about the arrangement of your conductors, there is also a way to calculate or predict the value of the capacitance. You can predict the capacitance. And the quintessential example, honestly the simplest, well, maybe, yeah, it's arguable if this is the simplest arrangement of conductors, but the parallel plate capacitor is an example of a simple situation where it's actually quite easy. Even if you don't know the charge or the voltage, actually you need to know both the charge and the voltage to calculate the capacitance. But if you don't know either, you can actually still calculate the capacitance. And so I'm going to show you this quintessential example. But then after that, I'm going to describe some generic things about capacitors, because it doesn't need to be any particular shape of conductor. They can just be random lumps of metal, right? And I'll be talking about, in the generic example, I'll be talking about the relationship between field lines, equipotential surfaces, an interesting device known as a voltmeter, and some ideas of sort of keeping all the ideas just straight in your head, like all organized in your mind. Okay, so that's what this video is going to look at. So let's introduce capacitance. So capacitance is given symbol capital C. All right. So a couple things. Well, actually, yeah. So C is defined as, so this is a definition of Q per V. So this is the definition. Q, I think it's actually better to go ahead and say Q separation, so separated. So this is the separated charge. I'll explain what that means in just a second. And V is really just potential difference. And I'll go ahead and say it now. I think a better way to do this is to say that the way you can calculate capacitance or define capacitance, it's equal to the charge separated divided by the potential difference, but only the magnitude of it. And the separated charge, we're going to always say that we're going to count the positive version of it. So what I mean to say is this capacitance is always going to be bigger than or equal to 0. So I think this is important to say. You should never have a negative capacitance. Strictly a positive notion. Okay, I don't think I'll run into trouble by saying that, but I'm going to say that this is how you should view capacitance. All right, so here's an example, and it's simple. So here's an example. I'm going to calculate the capacitance. So what is C if the separated charge is 3 coulombs and the potential difference happens to be, I'm making stuff up, it's 5 volts, right? So this is super easy to calculate, right? I'm given the charge and I'm given the potential difference, so I can just divide. And so this is what you'll do. So you'll take capacitance equals 3 coulombs divided by 5 volts and 3/5, right? And in the introduction to this video, I said that the coulomb per volt is referred to as the farad. So this is the capacitance, right? And I am done in terms of calculating the capacitance. So before I move on to my next example, which is a little bit, got one extra complication, let me draw a picture of this, right? So capacitance associated with 2 conductors. So here is a conductor, and here is a conductor. So this right here, these 2 separate conductors, this is my capacitor. So this is the capacitor. So I've got a conductor. That could be conductor number 1. It's some random shape, some random lump of metal. And this is conductor number 2, some other random metal. And then I have the situation where there is vacuum in between these 2 lumps of metal, or otherwise an insulator. And this is the sense in which a capacitor is 2 isolated conductors. So I have two separate conductors, and they are isolated from each other and from the rest of the world by vacuum or some sort of insulator. There is no conducting path from this conductor over to that conductor. Like, for example, there's not a wire, not a conductor that touches both at the same time. So they are truly two isolated conductors. And in this example, the charge separation is 3 coulombs. So if I look right here, I could imagine setting up this charge separation by going into conductor number 2 and removing 3 coulombs of electrons. So I'm going to remove 3 coulombs. So here it is. So if I take the 3 coulombs of electrons away from this conductor, what's left over is a charge of 3 coulombs. And I'm going to take this negative 3 coulombs of electrons, right? And I'm going to shove them, force them to all sit together on conductor number 1. So that means that the charge of conductor number 1 has become negative 3 coulombs. So here I have separated charge by moving negative 3 coulombs from one conductor to the other. And because of charge conservation, remember the conservation of charge? Because of conservation of charge, if I remove it from here and put it there, I can see the net conservation because I started off with no charge, and then, so the net charge is 0, and then after I separated the charge, the net charge is still 0, right? The total amount of net charge just didn't change from 0. So that's what's meant by separated charge. And when I did this, now I have some charge, right? So let me clean this drawing up and show you something about this charge. So I've got this is conductor number 1, and it's got the negative charge of negative 3 coulombs. This is conductor number 2. It's got the positive charge of positive 3 coulombs. So this sort of looks like a dipole, so let me write that word. But it's not exactly the sort of like standard dipole. I have a point charge and a point charge. Instead, I have these two, they could be macroscopic conductors, right? These two things could be the size of automobiles. This could be one automobile, and that could be a different automobile separated by air or something like that. So the metal of the car and the metal of another car. But anyways, so there is electric field between these two objects, right? Because they have charge, and this object's got field lines coming away. This object's got its own field lines. So the net electric field is the combination of the field lines, right? The superposition principle. And when all is said and done, you might have a picture like this for the electric charge. Remember that, the electric field. Remember that field lines have to come onto conductors perpendicular, right? So perpendicular, perpendicular. So this next field line, maybe it goes perpendicular like that. And then this field line perpendicular off the surface. Let's say it basically makes sense to go there. But the field lines point from positive charge to negative charge, right? So perpendicular here, perpendicular there. Anyways, so I fill out all these field lines, right? So this field line goes out into the drawing, so I won't draw it. And then this field line, say, comes around to that side, right? Okay, so this field line comes around to there. Anyways, here's the field lines. So with field lines, you can imagine equipotential surfaces. So the surface of a conductor is an equipotential surface. It's all one value of potential. And then you can draw other equipotential surfaces. And remember, equipotential surfaces are also perpendicular to all the field lines. Right? So That's one of the surfaces. Maybe there's a middle surface here. Okay, and then here's another surface real quick, some middle value, and then the surface of this conductor is all an equipotential surface. Yeah, so you get the drift, I think. Kind of looks like earlier lectures. So the thing is this capacitor idea is just a definition, charge separation divided by voltage, that sits on top of all of your previous ideas about electric force and electric field, equipotential surfaces, the value of the potential. And it must be that, do you remember, so in this example problem, it's 5 volts of potential difference. And so maybe I accidentally did this right. This would be kind of a cool thing. We could say, no, actually I didn't do it. So 1, 2, 3, 4. Oh, shoot. I wish I chose a different value. But anyways, one thing we could do is we could say that this surface here is the equipotential associated with, so field lines point from high to low, high potential to low potential. So let's say that this one at the high potential is positive 2.5 volts. And down here, this is negative 2.5 volts. That is the potential difference between the high conductor and the low conductor is 2.5 volts minus a negative 2.5 volts. So the total potential difference is 5 volts. And the charge separation is 3 coulombs. It still is this calculation. You get 3/5 of a farad for this set of conductors at that particular spacing with this insulator in between 3/5 farads. Okay, lots of stuff, but the equipotential surfaces, the field lines, the individual values of voltage, they're all at play in this world. Here's an example where the charge separation is more complicated. Okay, so let's imagine I have my 2 conductors. All right, and here is the idea. I'm just going to tell you the story, and hopefully you can kind of see what I'm talking about. So I'm going to start these 2 conductors off such that there is actually a net charge of 4 coulombs. So the way I'm going to assume that my world starts off, I can do whatever I want, but I'm going to start it off as 2 coulombs and 2 coulombs, right? So that's the charge of the conductor on the left, and that's the charge of the conductor on the right. Just 2 positive 2 coulombs, right? So net charge is positive 4 coulombs. Now I'm going to separate charge. So what I'm going to do is move 8 coulombs from the left conductor to the right conductor. So I've started off, they have the same charge, but now what I'm going to do is I'm going to move 8 coulombs off of here over to there. So once I remove 8 coulombs, right? So here is 8 coulombs from there. This thing becomes a charge of negative 6 coulombs, right? So if I remove 8 coulombs, then 2 coulombs minus 8 coulombs is negative 6 coulombs. So now this conductor has its charge changed, but I'm going to make this 8 coulombs, I'm going to put it on the right conductor. That's how I'm separating the charge. Move 8 coulombs from the left over to the right. So the left charge goes to negative 6 coulombs, and the right conductor's charge becomes 10 coulombs. but the charge separated is equal to 8 coulombs. The charge separation is the 8 coulombs. So the charge separation is not the 10, it's not the 6 or the negative 6, and the charge separation is not the 2 or the 4, it's actually 8, because that is how I made the charges different. I made it different by separating 8 off of one and putting it on the other. So this is really a complicated issue. So the charge separation is 8 coulombs in this case. So let me give you an example that's backwards, because it tends to, in problems and test questions, it tends to come in the reverse order. So the example I have in mind is this one. So calculate capacitance, for these conductors if, so I'm going to just give you the data in a picture. So I've got this conductor and this other conductor. So I've got these two separated conductors. Turns out that the charge here is positive 2 coulombs, and the charge here is negative 8 coulombs. That's just the charge of the two conductors. But neither of these charges is separation charge. So I've got to figure out the separation. But another thing, so these are the charges, and the potential difference is given by a device called a voltmeter. So it is a device that measures or meters voltage difference. And typically in diagrams, the voltmeter is a little device. Maybe I'll draw it as a square or like a rectangle. And this little rectangle has 2 wires. And what you do is you touch one of the wires to one of your objects, the other wire to the other object, and what this does is it tells to you the potential difference, difference between the two objects. So let's say that my voltmeter in this particular example reports a potential difference of, let's see, my example has 8 volts. Okay, so 8 volts of potential difference between these two charges, or these two conductors whose charges are 2 coulombs and negative 8 coulombs. So when you go to calculate the capacitance, you've got to put in the value of the charge separation divided by the potential difference between the two objects. The voltmeter tells me that the potential difference is 8 volts, so the bottom is really easy. Right, that's the value on the bottom. It's 8 volts of potential difference. But the separated charge, this is the hard part. So what you have to do is, the easiest thing to do is this. So Q net is equal to, right, 2 plus negative 8 is negative 6. So the starting point is negative 3 coulombs and negative 3 coulombs, right? So if this starts, at negative 3 coulombs and this conductor starts at negative 3 coulombs, the charge separation is, how do I convert negative 3 coulombs into positive 2 coulombs and negative 8 coulombs? You can see that if I start with negative 3 coulombs, or actually, let me start here. If I start with negative 3 coulombs, the way that I go up to 2 coulombs is by adding 5 coulombs. Can you see that if I was able to add 5 coulombs there, then 5 coulombs plus negative 3 coulombs is the ending charge of 2 coulombs. But that 5 coulombs must have come from this side. So minus 3 coulombs, subtract off 5 coulombs, is the negative 8 coulombs. So 5 coulombs was the separation charge, right? So in order to get to 2 coulombs and negative 8 coulombs, I must have started with the same charge. This is the situation where there is no separation of charge. I start this way, and then I separate the charge by moving 5 coulombs from here to there. That's how I separate, or that's what I did. So, or that's what I must have done. So this is what belongs there, and the capacitance is equal to 5 divided by 8 farads, right? So this is complicated. It's not complicated because of the voltage. It's actually complicated because of the charge separation. Okay. So the last thing I wanted to describe is this is important. So important conceptual idea that's hard to prove, but important, right? And that is capacitance, which granted is charge separation divided by potential difference, right? That is what it is. But C is actually independent of charge and voltage. What happens is this ratio the ratio Q per V is purely a geometric and materials. So I'm going to, geometry and materials issue. So, geometry refers to shapes of conductors, right? Cylinders or spheres or planes or lumps. You have to precisely describe the lumps, right? But geometry refers to the shapes of the conductors as well as distances, right? So all of the geometric issues, like what are the shapes of the conductors and how far apart or how close to each other are they, right? And in what orientation, like, you know, are the two lumps like this, or are they like this, or are they like that, right? So you can have the same two lumps, but if you change, you know, how their how their position or orientation relative to each other, you may also be changing the capacitance, you know? So the capacitance is an issue about anything geometric, shape or separation distances. Okay, so geometry refers to shapes of conductors as well as distances. Materials, though, are, remember up here I say capacitance is independent of charge and voltage. Actually, this ratio, which is the capacitance, is purely a geometric and materials issue. So the materials issue is about the vacuum or insulators that separate the two conductors. So the conductors isn't really the materials issue. The materials issue is really the choice of insulation that isolate the two conductors from each other and from the environment. The word that comes up later, and I'll likely talk about it in the next video or the following video, it's called dielectric. Dielectrics are a material issue, and you can use dielectrics to change capacitances. And so this is a pretty cool thing. Okay, so the last thing I wanted to describe was the quintessential example of calculating capacitance. That is, we are going to predict the capacitance without knowledge of either voltage or charge, just geometry. In this case, we're not going to have a material issue because we're going to be working with vacuum, and vacuum quite literally is not material. So that's a joke. So just geometry. So the example, the quintessential example, is called the parallel plate capacitor. And the parallel plate capacitor is an idealization. So I'll describe what's meant by idealization. So here's a drawing of a parallel plate capacitor, or at least a diagram. What it is you have one metal plate. So what I'm trying to do is draw it so that you can see a little bit of the perspective. So here is an edge of this metal plate. Right, I hope you can see that. And let's say that this is like an x-axis, right? And the other plate, yeah, I'll just draw it over here. So the other plate is really close. It is parallel. I hope you can see what I'm drawing. So this is like an outer edge and this is like an inner edge. Can you see that? Just two plates like this. They're separate, right? Isolated from each other by vacuum. There's vacuum in between. And this picture is them like tilted a little bit. They're still parallel. Yeah. So this distance here is the distance between the plates. I'll call it little d. And then the plates themselves have area A. So both, they are the same plates, same area. They are separated by a distance d. The idealization is that this distance d is really small compared to A, that is the area, but it's the square root of the area. And what I mean by that is, you remember for a square, right? The area of a square is the side length squared. So the idea is if I take the square root of the square's area, right, what I get is the edge length. And what I'm saying is that the edge length of this parallel plate capacitor, either the top edge length or the side edge length, either one of those is really, really, really big, right, compared to the separation distance. And in this idealization limit, the plates can be considered infinite, right? So these are infinite conducting planes of charge, if I separate charge. Okay, so I hope you can see, maybe this will help actually, if I continue the x-axis. So the x-axis, yeah, maybe that helps you see the separation. All right, so notice there is no mention of charge or voltage. So how are we going to calculate the capacitance if I don't know either the top or the bottom, right? So this is the goal. I want to predict what is the capacitance. So what I do is I start off and I say, well, imagine that I separate charge Q. So in order to do that, right, so this is how you start. You just imagine a separation. You could choose a coulomb or a microcoulomb or 50 nanocoulombs. You can choose a random value, but you got to choose one. So I'm just going to choose a like a symbol for one. That is, I'm going to choose a variable amount that I can choose anything. So I'm just going to choose something called Q, and if I need to, I can stick in a value for Q later, but I'm going to show you that I don't need to. It's pretty cool. It's actually that the capacitance is independent of my choice of the charge. So I'm just going to imagine that I separate something called Q. So I'm going to put that the positive Q is here. That is, I'm going to steal charge Q from the right side and move it over to the left side. So that's the separation. I started off with neutral plates and I separated the charge Q, and this is the end result. So these are infinite plates, and a really nice thing is to talk about the charge density, right, the charge per area of the individual plates. So this plate is going to have charge density sigma because it's got the positive charge, and this one's going to have negative sigma, where the surface area charge density is equal to, it's the charge divided by the area. So we're going to imagine smearing uniformly the charge Q over the area of each individual plate. Over here, I've smeared the charge negative Q over the area A. But this is what sigma is, and one of the plates has the negative version of it, right? Okay, so I'm going to move these details to another piece of paper, and I'm just going to draw this parallel plate capacitor edge on so that we don't have any perspective. I just wanted to show you that this really is just two pieces of metal of a special shape and a special separation distance. So here's the x-axis. Here is one of the plates, and here is the other plate. And I know there is a distance d between the plates. These are of area A. This is the positive sigma plate, and this is the negative sigma plate. So Gauss's law. So you see, we're talking about electric field, right? We're talking about infinite planes of uniform charge, surface charge density, and all kinds of stuff. So Gauss's law is relevant, and I'll show you why. So Gauss's law is really useful in this situation. The electric field due to the positive sigma plate, right, it's got a magnitude. So I could do the magnitude of the electric field due to the positive sigma plate is just sigma over twice epsilon naught. The electric field due to the negative sigma plate, if I want the magnitude of it, it's actually also, right, and be really careful, I'm talking about magnitudes, it's also sigma over twice epsilon naught, right? Magnitudes are strictly positive quantities, but you have to be really careful. So let me show you how to be careful. So if you just look at the left-hand plate has electric field, right? The left-hand plate is positively charged, and field lines point away from positive charge, but for this plate it points towards the right on the right-hand side, but on the left-hand side it must point to the left because this is all positive charge, and field points away from positive charge. So this thing, though, this is negative, and field points towards negative charge. Right? So if it points towards, that means it points left on the right-hand side and towards the right on the left-hand side. Okay, but check this out. This is also how, so this plate has electric field also over here that points towards the right, which means that over on this side of this left-hand plate, the field of the left-hand plate and the field of the right-hand plate are going to add up to 0. So the net electric field everywhere over here is 0. The net electric field everywhere over here is also 0. But in between the two plates, the field only sort of enhances each other. They combine up, and the electric field is of one of these and the other. And so when you combine these two things, the net electric field between the plates equals sigma over epsilon naught. So this is the electric field between the plates. The potential difference between the plates, it's as simple as doing this. The electric field is sigma over epsilon naught, and the distance between the plates is d. And I'll remind you that delta V is equal to, what you have to do is you take an integral from one place to another. You take the electric field, the net electric field, and you dot with displacements that take you from initial to final. So the way that we'll use this situation here, and also, so I'll just kind of say this quickly, but just go like this. Start here and go over to here. And so if you start here as the initial and this is the final, the electric field has a value that's independent of position, right? So it doesn't matter what the values of x are in between, because that's the magic of Gauss's, or that's the magic of the electric field of an infinite plane of uniform charge density, that it's independent of location. It's a uniform field. So anyways, if you do this, you can get to the fact that the potential difference between the plates will only ever have a magnitude. And I'm talking in particular about this minus sign and being careful about minus signs. But it'll have a magnitude that's equal to this. That's the potential difference between these two plates for a given choice of charge separation. And so what you can get from that is you can say, well, I've got potential difference. I imagined separating this charge Q, which is where sigma comes from. So if I go and I calculate capacitance, I imagine separating the charge Q, and there is an associated potential difference delta V. The charge Q, another way to write it is sigma times A equals to Q. So I'm going to write it instead as sigma times A, right? I'll put that there. And then I divide by delta V, and delta V is sigma over epsilon naught, and then multiplied by D. Right? So what happens is this epsilon naught goes up to the top because it's divided on the bottom, right? It's 1 over. So in the bottom, it flips to the top. So, and the sigmas cancel. Sigma cancels, and I get this. And I'd like you to notice that it is independent of the choice of charge separation and the associated potential difference, but it depends on materials, in particular, the fact that we are talking about vacuum. This is the signal that we're talking about, vacuum. We're talking about the vacuum value of what's called the permittivity of free space, and geometry. The geometry of the plates is that they have area A and are separated by distance d. And that's the only dependence I see in the capacitance.